Raju Venugopalan, visiting us from Brookhaven. Give us a talk. Raju will not know what to do wrong. He was an undergrad. So he broke it up. That Brookhaven National Lab, then his research has been planning. Today is going to tell us about two-to-n scattering in QCD from gravity.
So I can just use speak. Oh, sorry to bother you. Anyway, it's a pleasure to be here, and so on for a very long time also. And among the many remarkable things about Son is that he takes my last name perfect, which is a very rare thing. So that's something. I have a nice story about how you were in that regard, but I'll tell you later. So anyway, so this is the title of my talk, and so you know my interest in some of these aspects of gravity actually arose from thinking about scattering in QCD. And so normally you would say, well, these are very different theories, but they have a lot of very interesting common features. And in fact, there are some exact double copy relations between QCD and gravity that we developed. Thanks so much. There's some double copy relations that have been developed, which really show that there is a mathematical correspondence between QCD amplitudes and gravity amplitudes. And I find that really something really spectacular. That's something that describes physics on the scale of 10 to the minus 19 kilometers. Might have something to say about something that happens on the size scales of billions of kilometers. And so this is really quite a striking thing, and that's what kind of piqued my interest in this topic. Let's see. Thinking now. There's a circle. It's maybe I should get rid of. Oh, yeah, it's the it was sitting there for too long. We looked at it.
Let's share again. Let's stop sharing.
Back to the stop.
Okay, so we do the.
Okay, so now screen. Oh wait. No, that's the wrong. That's what I thought I had open, so let me, so I think my PowerPoint is. Okay. This is oh. This is not. Right. That's always kind of force. Okay, okay, sorry. No, okay, sorry about this, everybody. So anyway, what I want to mention is that there's been for some time understood that there are quantitative double copies between QCD amplitudes and gravity amplitudes. And this goes under the name BCJ, Bern Carrasco Johnson. And its precursor is a relation in string theory called the KLP relations, the collide-implied relations between closed strings and sums or products of open strings reaching a low energy limit relates Yang-Mills amplitudes to Einstein amplitudes. So that's the underlying reason. And so BCJ have actually developed quite a quantitative theory of this, and this is actually now state of the art in trying to understand the in-spiral regime of black hole mergers. People use these techniques developed in QCD, apply the double copy technique, and actually calculate the in-spiral to sort of close in Gaussian order, G to the fourth, or even probably even higher by now. So this is really quite a successful program. Now, what I'm going to be talking about is a different regime where when you take QCD at very high energies, you enter a regime of very high occupancy. So the quark and gluons, in this theory, they start to proliferate as you go to high energies, and at some point you have very high occupancy ionic matter, and that's the regime you see at high occupancy. And then there's a question, and so that's a regime of very strong fields in QCD, where the occupancies are one over the coupling, actually. So it's very non-perturbative. And in that regime, you can ask whether there is a similar kind of double copy between QCD at high occupancy and gravity at high occupancy, where you have a system of many gravitons which are over-occupied. And so there's some work along these lines by these folks here, Goldberg Ridgway and Montero et al. And there's also quite a bit of work after there in this direction. Okay, you know what? I think it's actually it's PowerPoint, so maybe I should just make a PDF out of it.
I would think that the site you share the text software, if you share the software, then yeah. Share the desktop and make it public screen.
So you mean if I send it to him? For
Yeah,
example?
I mean like I don't know if you
So on the he mentioned on the team,
share desktop.
Let me just
Or
make
like share.
sure. We first get rid of Microsoft Switch. I think PDF might work actually. So PDF is much easier. So let me save this as PDF. So process. Yeah. Here. What is this? And then maybe you have to click on this, yes, to make it bigger. Okay, great.
Oh.
Okay, so now, just to really quick. The third thing, so the process that double cup.
Right.
The large ends, where it works, we can even run this one. No, it's actually QCD itself. Yeah. Okay. But I mean, so it's gangles. Right. So pure glue and gravity, statement about the estimated system. Right. So it's any end.
But not the plate, not like.
No. So, so this actually has, you know, a bit of a long history, and part of my goal is to resurrect some work by Lev Lopatov, who some of you may have heard of, who is this great Russian physicist who died a few years ago, and to point out that actually he had these ideas of double copies well before these famous KLP, Hawaii relevant pi relations, in a somewhat different context, but he pointed out some really interesting double copy relations, and that's what I'm going to be talking about mainly. And so this was so what he did was he constructed vector actions, right, for high energy processing QCD and gravity, right, in high energy kinematics. So this is sometimes called multi-Regge kinematics. And he found that he can write these as sort of effective field theories in 2 dimensions, right, because at very high energies there's a separation of transverse motion and degrees of freedom. And this was kind of taken up by Amati, Ciappoli, and Veneziano in papers starting already from the late 80s. And they sort of developed the entire program, sort of lasting for 30 years. So I think I have some comment about that here, right? So there's about 30 years of this work, and that's kind of one of the leading ways to think about gravitational scattering, gravitational shockwaves, and also an approach to thinking about, say, black hole formation. And so at the same time, you know, as this paper, slightly later, there was a paper by Susskind, which is extremely highly cited. So I think it has probably over 4,000 citations since when I looked, where, you know, which kind of spelled out the origins of these holographic ideas. And if you read the paper, it's all about the physics of weak partons. So the physics of partons in gravity, so these are soft gluons and soft gravitons at high energies. And so it's really the question about how do soft partons behave under boosts. And so his idea was that somehow they form a kind of surface, okay, where all information is gathered on the surface. And so this 2D surface is a hologram of the 3D world, which contains all the information, so all the microstates of material concentrated on the surface. So that was kind of the original idea in holography, but it was all in the context of really thinking about these problems and how their words subtracted. And he actually thanks Lopatov in this paper, which is extremely highly cited and has influenced a lot of work in holography. And so let me kind of go back to high energy scattering QCD. So I understand that not everybody's familiar with this topic. So if you have any questions, stop me at any point, and I can go as slow or as fast as you like. So if you ask, you know, how do you produce lots of particles of QCD at high energies? And so that's done through something which is called the KL equation. So that's L in there is the Pareto again. And so you're looking at some 2 to N process where you produce N gluons. So you have 2 incoming, you know, quarks, so gluons, if you like, and then they produce, you know, further N gluons. And so this is a very complicated thing to calculate. So we think about computing amplitudes, right? It's a very complicated amplitude calculation. But you can work in a kinematics, which is called multi-Regge kinematics. So the momenta of these produced gluons, which are on shell, can be characterized in terms of their transverse momenta and an observable called rapidity. So you can roughly think of it as a longitudinal momentum. So it's the log of the momenta. And the multi-radial kinematics assumes that all their transverse momenta are roughly the same, but there's a strong ordering in their rapidities as you go down this kind of ladder that's shown here. And so you can say, well, what's the point? And the point is that when you look at such a construction, right, in QCD, the theory of logs, so there's lots of logs and different amplitudes. And it turns out that these give you the dominant logs to all orders in perturbation theory. Okay, so you get logs of x, which is the momentum fractions of these gluons that are produced, or they're proportional to the rapidity. So for each rung of the ladder, so if you look at this naively, right, you'll say, well, don't you get a huge suppression, right? You have alpha, large numbers of powers of alpha, so you think naively, oh, this is highly suppressed to some high power of alpha. But the point is that the alpha is accompanied by terms to linear rapidity, or logs of x. And so when the rapidity separations are large, the y's compensate, the rapidities compensate to the alpha. And so these are all processes of order 1. So 2-to-n scattering at high energies in QCD is an order 1 process, which is remarkable because you think about QED, it's not until you get to extremely high energies, right, where production becomes extremely copious that you get multi-particle production of this sort, right? So if you thought about photons and you're producing pairs of quarks, you have to go to very, very high energies for this to become order 1. Well, in QCD, it happens at realistic energies. So these produced partons in this 2-to-n language are what we would call B partons, because these partons, their momenta, logical momenta are ordered. So imagine that you have some very fine particle coming, and it's producing gluons, and those gluons are producing further gluons, and so on. And each of them is a little bit slower than the other. Okay, so there's a whole sort of string of slower gluons that's accompanying this very fast gluon, and likewise in the other direction, and that's how the scattering happens. So this is what's called the Regge regime of QCD. And it turns out that there's a renormalization group description of this amplitude, where you can think of this as iterating a given rung of the ladder. So you can think about that as you compute observables at one rung of the ladder as a function of this rapidity here, and then the Achilles equation tells you that how this ladder evolves as a function of changing the rapidity. And this evolution is given by something called the Achilles. And that turns out it's an object which has really beautiful properties. Okay? So it's a formal object that's very interesting. You can also compute an n equal to 4, supersymmetric Yang-Mills, and there's a whole sort of sub-community of people who actually work on these things here. And so what you find is that when you solve this, you get very rapid growth of the amplitude of the energy, where the amplitude you can write in terms of nanostam variables S and T. So this goes as S to some alpha P. And where alpha naught is what's sometimes called the Pomeron intercept. So it's the gift of the Pomeron. And alpha prime is the universal exclusion. So this actually tells you that, this is kind of a stringy-like object that it has. And this is the QCD recoupling counterpart of something called the non-filtered Pomeron, which we believe controls total cross sections of QCD at high energies. And there you can think about this alpha prime as really being kind of related to the string tension in sort of Yang-Mills, non-perturbed string tension of pure Yang-Mills. But in this case here, this is kind of a recoupling construction. And so this tells you, though, that the amplitudes go very rapidly with the energy. And this is what we see in experiments. Okay? Experiments receive it in cross sections extremely rapidly, and then you have copious multi-particle production. And in fact, that fundamentally explains why you produce lots of particles at the LHC.
So
yeah.
PL at the 0 is something constant.
I have it on the slide. I'll show you.
But alpha prime, something.
So yes, you can actually calculate alpha prime perturbability, but it's actually it's a highly non-trivial thing to calculate. Right, so usually the total cross sections are equal to 0, right? But in principle, there are calculations. And also depend.
But how do you say energy scale?
So this will also, there's alpha prime. Yeah, you're saying fundamentally it should be something that is proportional to some sensitivity to yeah, it will probably depend on some of the initial scale of your process that you put in. Right? Will certainly so the initial scale of your Parton distributions that you define, that's the scale of the sensitivity. This is the amplitude for, say, 227. If I want to, or so if I, so okay, so very good. So I can think about it as the imaginary part of the shadow. In that case, that would correspond to that.
You're integrating over to one.
Exactly. So you can do the calculation two ways, which is you take the imaginary part of the two scattering amplitude, right? Or you can directly compute 2n and then integrate over. So, but that tells you about the cross section for the reflection from the optical field. And so you can ask, what are the building blocks, right, for this process? So if you recall, I had these lines here. Sorry, I had solid curly lines being exchanged, which normally look like that of gluons, right? And then I had these red blobs. And so the important thing to keep in mind is that these are effective propagators and effective vertices that are giving me this instruction, this vehicle instruction. And the way to think about a given rung of the ladder is that I'm summing over all possible ways in which I emit a gluon. Okay, so if I'm just looking at one rung of the ladder and producing a gluon at that rung, and then I'm summing over all possible tree level diagrams to do that. And then you can use the Jacobi identity to rewrite that as some non-local effective vertex. That's called the Potter vertex, and that's given by this expression here. So even though it's written as being also proportional to U and P2, you could show that this can be rewritten in a way that only depends on the transverse momenta of these exchange particles to construct the ladder. And this is the nice thing about this is that it's a gauge covariant object. KU times CU is 0. And so you can sum up all these possible contributions that you can get. While the other contribution, which is this Reggeized gluon exchange, can be thought of summing all possible such ladder diagrams, which correspond to these loops here. Okay, so in principle, you have sort of two gluon exchange loop, right? And then you can iterate this to all orders. And in doing so, what you're doing is you're replacing the bare exchange of the propagator, which is 1 over T channel, with something that resums all of these contributions. And so just at the next order, this loop contributions here, they give you essentially this string tension here. So the answer to your question, actually, Son, is that this has an infrared divergence. So it has some infrared divergence, which depends on the scale in theory. Okay, but when you actually then calculate total cross sections, it's cancelled. So at this next order, right, you get this logarithmic contributions, which are of this form here, and these
cancels out. To go back, if it cancels out, I think the final answer.
yeah, when you compute total cross sections,
So the 2 to 2 inclusive of any subgluons.
right?
What is the
So you would compute sort of all the real and virtual contributions. So the total cross section is would be cancelled. And we infer.
I see. So you don't have a cancel That's easy to say, just a final number.
Yeah, well, no, you would not see any dependence on the incorrect scale. So there's a trade divergence, you just sum around the QCD scale, right? You say, well, it depends on the QCD, right? But then when you go back to your cross section, it's independent of this.
Total cross section, does it know about only alpha zero or it knows about alpha prime?
So total cross section only knows about alpha. So, yeah,
Alpha prime.
there's alpha prime doesn't contribute to the total cross section, but if I'm
Because
computing
T has been
any,
integrated.
yeah, if I'm computing any cross section, right, then there's a cancellation of virtual and real divergences. And so these incorrect divergences cancel.
Still, so this alpha prime is still somehow be related to some skill in this integral. Depending on how this integral is.
Well, so it depends, right?
On the size of your.
Right. So there's a resolution scale. So this is the usual square divergence. Yeah. This is the Bloch-North-Seek divergence. That you get the QED as well. Sorry? Usually it's not nice. It's usually what we're.
Like,
So if well, it's a logarithmic divergence here, right? But there's an explicit, so you would get an explicit dependence, right, on, so essentially what you'll find, sorry, I have the answer. So, yeah, so what you find is that when you compute this, you'll get a term which will cancel this t, and then you have a log. Rewrite this in such a way that I can take out u squared, right? And that will cancel the t, right? And there's a residual log with t. You'll never get to this fertility calculation. Harlow. So I think that's the answer to, sorry, I got a little confused there for a minute. Right, so that you can pull out the q square dependence that cancels this t, so there's only a residual, and that's the sort of problem. And that you can exponentiate to all numbers. And so if you're now computing, so as I said, there are these building blocks, right, which are, yeah, so there's these building blocks which are, 2 to 3, the things that are the effective vertex, and there's things that come from the reggeization resummation. And then you can put these two together to construct the full 2 to n amplitude. And the way to see it very nicely, right? So here's your full ladder. So, but you take the imaginary part, right? And so that depends on, say, there's some powers of alpha and color factors. Then there's a phase space factor. So this is the phase space and rapidity. That's an invariant in v squared keeper for each of the objects along the rungs of the ladder. There's the Regge propagators on both sides. So there's 1 over t, 1 over t prime on each side. There's the exponentiation of this loop correction. So this weekly line here is resumming to all orders of perturbation theory, all possible loop contributions, and that's in this one here. And then you have the product of the Lipado vertices, which are these black blobs here, and this is gauge invariant. So this is a completely gauge invariant construction. Okay, and so these gluons, so these are these so-called regions that are being exchanged in each channel. And then this cut propagator gives you this total cross section, as I mentioned earlier, and this cancels the vertex. And this is also the answer to you for the intercept. So that's given by alpha s and c log 2 and prime. Okay, so it's a number, which depends on alpha s. And you can see that for some realistic values of alpha s, this gives you a very rapid. Now you can extend this program to next to leading log accuracy. So this is all orders of perturbation theory, but it sums leading logs, which are powers of alpha times y. Okay, and so because there's an alpha here, as I mentioned, and so it resums all orders alpha y. Now you can extend this program to next to leading log as well. Okay, and that's called analog scale, and that reduces this intercept, but it's still a very rapid growth in the cross section. Okay. So what this is telling you that when QCD, when you're high energy scattering, these gluons, and they love to proliferate. And in fact, the Affiliation equation is a kind of Markovian equation that when you change the number of gluons depends on the number of gluons at the previous step. And so it's a general Markovian process, so it gives you an exponential growth with the rapidity. That's shown here. Okay, so that you can rewrite this as just a power lambda. Now, so what happens, right? So imagine you're going to higher and higher energies, you're producing more and more gluons. They're bigger and bigger gluons. They're slower and slower gluons. And so the question is, does the cross section explode? You violate the Broussard bound high energy scattering. Okay, so in fact, if you solve the BFK equation, so this is now the BFK amplitude written in sort of slightly different way, right? So as a function of momentum in the forward limit. If you plot this as a function of transverse momentum, and say you start out with some initial distribution which is strongly peaked in the ultraviolet, right? And then you solve this BFK equation, you find that the result has this kind of boosted distribution. Okay? So it has some diffusive property, and you find that as you go to higher and higher energies, the solution actually goes into the infrared. So the solution kind of violates this perturbative assumption of its construction. And so this is, so the another way of saying it is that the operating part of extension, which is the basis for this construction, is actually breaking. Breaking down in the sense that higher twists are becoming important. So higher twists are becoming important. And so to regularize the theory, you have to include all these higher twists. It's not that there's a long OP, it's just that higher OP corrections are becoming very important. And what this is saying, another way of saying it is that you can work with an arbitrarily large momentum transfer, right? So where perturbative QCD should work, right? You can start with some KT, which is very large. And the statement is that if you go to sufficiently high energy, right, no matter how high a KT you started with, where OP should work, right, you have this distribution to the infrared. And so going to next to leading log doesn't cure this problem. And what cures it is a phenomenon called gluon saturation. And what that is that imagine you have this ladder of gluons, and you can have additional such high twist configurations where two ladders can fuse to one. So you can think about this as, you know, gluons producing softer and softer gluons. But at some point, the density of gluons gets so large, right? It's a many body system where you can have squeezing and recombination of gluons going on, which actually change the number of gluons, so that you can sort of producing more and more gluons to have two soft gluons fused from a partner. So that kind of depletes the number of gluons. And so if you do all these kind of higher twist contributions, you'll find that this stabilizes this cross section when the occupancy of gluons is on the order of 1 over alpha. So what you're saying is that this intensity quantum mechanical process, right, well, the theoretic process will produce lots and lots of gluons, at some point leads to a possible state. And this is a state of very high occupancy and is characterized by an emergent scale. Right? Oh, it's order. Well, that's parametric. It's telling you that when you look at configurations, that integral of the exponentials. And so this is arrived at the recoupling. You recover something that's non-perturbative because you sort of otherwise just use naive perturbation theory. You just get something that's a power series in alpha, but because you're also doing resummations at each order, what you find is that they get very high occupancies that you bring all order resummations, which give you an occupancy which is order. So what this tells you is that there's an emergent scale in the theory, okay? And this scale can be very large. So if you go to the Regge limit, the scale can be larger than any of the scales in the theory. So And so the coupling to speed runs as a function of the larger scale. And so this is recoupling physics. So there's a self-consistency that you start with some consumption, right? You solve the theory, you see that very high energies, you get this emergent scale. And so but that tells you that the physics of this many body system is essentially classical, classical. And so this is kind of a cartoon which illustrates what I'm saying. So imagine you have on the y-axis boosts, so you're going to higher energies here. So you're boosting to higher and higher energies, so logs of the energy. On the x-axis, you have resolution. So how finely you're resolving what's going on inside your hadrons or whatever objects that are scattering. The statement is that in this context of this cartoon is that you can start with arbitrarily high q squareds, where you have really point-like partons. Okay, so these are partons in the theory. And then the partons, as you go to higher energy, start to proliferate because of this BFKL Markovian evolution. And then at some point, right, you reach a state of maximal occupancy. So phase density becomes as large as it can be in theory. And so you can't, put any more stuff in. And that's a kind of unitarization boundary. And that occurs when n is, I put here in the approximate sign. It's a 4 to 1 direct. And so this happens for any given q squared. So that tells you there's a line, okay, in this energy resolution plane, right, which characterizes this emergent scale. Okay, so in other words, the saturation scale here is the scale, the resolution scale of any given x, right, where unitarization is. And so this is kind of a striking thing because it's telling you that even in decoupling, right, for arbitrarily small sized objects in QCD, they will act with, with unit probability, right, at sufficiently high energies. Because the object that gets scattered with is so dense that even though, these are very weakly coupled objects, they scatter with lots of stuff. Right? Each individual scattering is very weak, but they simultaneously scatter with a lot of groups, right? So this is like a lot of problems in condensed matter physics, right? Where the coupling, fundamental coupling is very weak, but because you have an in-body system, the effective coupling is very large. And so you have very strong interactions. And so it's saying that in QCD, where there's such a condensed matter regime, where the effective coupling is very large, even though the fundamental coupling is very weak. And so there's an EFT, which describes this physics, this regime here. And that's called the color glass condensate. And it's a very powerful sort of RG picture, which describes what I've called so-called states. So in the classical Regge language, these kinds of multi-ladders that I showed you, these are like multi-Pomeron ladders, the old Regge language. And so these can all be kind of described by this EFT. So where you have sort of, so if you think about some probe that's scattering off the hadron or some other final states, you can have all possible sort of scattering and recombination diagrams included in this stuff. With the prejudice that what you're starting from is a highly occupied semi-classical state. So this is a state of very high occupancy described by an emergent scale. And so you can actually calculate all n-body correlators. So it's very non-perturbative, but recoupling, but we calculate precisely because alpha is very small.
Is there an actual Hamiltonian spectrum? Is there this kind of
Yes,
twist?
yes. It's called the Blue Hamiltonian. It's a generalization of the FPL Hamiltonian. And it describes, so you can, describes the evolution of n-point groups of line orbits. So you get something like the action of Hamiltonian generates something like the EGKY hierarchies at that, where you have 2-point correlators, 4-point correlators, and so on. So you have infinite hierarchy, which the Hamiltonian describes, which we can actually solve this. And the reason you can solve it, numerically, it's very not trivial to solve analytically. The reason you can solve it is that it's an effective 2D theorem. So precisely because you have the separation of scales within one. And so all the non-trivial parton dynamics, many body correlators, partons, at very small distance scales inside of hadrons are being described by the 3D. So it contains very complex non-trivial dynamics, and it corresponds to a non-trivial logical form. So you can in fact understand this in the saturation scale as the non-trivial, as the scale that characterizes the non-trivial. And so you can actually, but so imagine trying to compute all of this using amplitudes in possibly difficult calculation. You have lots and lots of millions of cuts. And so in the semi-classical picture, if you replace all of this complex amplitude, so think of this as some very complicated amplitude, at high energies, you can replace that by a classical field. It's a color charge density. And this color charge density is a classical color charge density because it lives in some higher dimensional representation of the algorithm. So if you think about your young tableau and you multiply lots of 8s or 3s, right, you'll find that you will very quickly generate a distribution of representations, of which the most likely representation is some higher dimensional representation, and that's a classical representation in theory. So the sum over all of these, all of these color factors in this very complicated amplitude can be replaced by some classical color charge density. And so this really then gives you a classical effective theory, which you can then compute in principle systematically. So let's take a very specific example to illustrate what I mean. So imagine that you have some virtual photon that fluctuates into a quark and gluon pair, quark anti-quark pair, and that scatters off all these n gluons that I formed at the bottom of the ladder, say coming from another hadron. And at very high energies, that's like a shockwave. That's like a classical gluon shockwave. And so the classical scattering amplitude is that of this quark anti-quark dipole, which scatters to the shockwave, which is moving along the other light cone. So this is at very high energy. So the dipole is moving along one light cone, and the quark and the gluons from the other hadron are moving along the other light cone. And so this is a shockwave scattering where these blobs indicate the points of interaction. Now, at very high energies, you can describe these in terms of Wilson lines. So you have coherent multiple scattering of all these gluons, which can be replaced by a Wilson line correlator. And so the cross-section for this is just described by some trace of product of Wilson lines at some position x and some position y. So it's V dagger at x and y. And so now you say, okay, this is a classical picture. What happens if I now go to the next order and I emit a gluon? And so this gluon can also interact at some point z. And so when you compute this one loop correction, you can rewrite this amplitude as a function of the change in boost. So this is at some energy. Now I boost the energy. And as I boost it, I can emit a gluon. And so I say, how does this amplitude change as a function of boost? And that's described by this nonlinear equation here, where you see that this 2-point correlator is proportional on the right-hand side to some kernel. And this is now just a 2-point correlator itself, right? So it's related to 2-point correlator on the side, right? But then there's also now this 4-point correlator. So, however, in the very high, so this also depends on this additional positions in perp here, where the gluons are in it. Now, it turns out that if you now take large NC, and you take an initial condition, say a large nucleus where the initial condition factorizes, then this expectation value of the product of two Wilson line correlators can be written as a product of expectation values. And so then you get a purely nonlinear equation for an object which is of this sort here. This is sometimes called a dipole amplitude. And so you get a dipole amplitude which is n is proportional to n minus n squared. Now, if you just kept the n term and you threw away the n squared term, so if you just kept this term, that is the BFK of it. And that is the Markovian equation that I was mentioning. I say because a change of n, which is this, with y is proportional to some kernel acting on n. Okay, and so this then is what gives you the Markovian rule. But then, because you have this nonlinear term, that gives you a non-trivial fixed point when this term is equal to this. here. So in other words, when n equals 1, there's a fixed point where the derivative of this goes to 0. And so that defines this emergent scale and all this classical behavior. And so you can understand this, again, in the language of scattering, as saying that instead of just having one Pomeroy ladder, you can have multiple such fan diagrams. So you can have a Pomeroy split into many other Pomeroys, and so it's in terms of, and this is sometimes called a triple Pomeroy vortex. And so this is really the content of Regge field theory. So this is what kind of describes a lot of physics in Regge field theory. So, so this is kind of a very powerful formalism, gives you a non-trivial scale. And so you can actually look at what this distribution looks like. So if you remember, I mentioned that you have this problem of infrared diffusion, that you had some initial distribution of the Hamiltonian. As you went to higher energies, it was diffused in infrared, and the OE kind of broke down. However, if you now solve this nonlinear equation with some initial distribution, which is peaked at some large momentum, you see that this actually moves outwards. So it actually satisfies traveling wave solution. So it's like a solitonic traveling wave. And in fact, this equation that I mentioned to you, the decay equation, is to a very good approximation the same as the Fisher-Kolmogorov equation for traveling wave fronts in statistical mechanics. It has all the features of the equation, and that sort of describes the evolution of this object here. And this is how one can understand this close backing scale. As you go upwards, you know, it's the peak of this distribution, and you see the peak of the distribution goes outwards as a function of energy, and that's this saturation scale that I mentioned earlier. So this kind of solves part of the problem that I was mentioning, that it cures infrared diffusion by requiring that the theory forms a closely packed state in infrared, very high energies, which is leading to this emergent scale. And the remarkable thing is you can compute all of this, right? It's many body physics that you can compute in recoupling. And so you can look at more complicated correlators, and people have done that. And so the state of the art in high energy QCD is, so the nice thing is you can do experiments, and you know, you have to compare these things to experiment. And the state of the art is now, instead of just this dipole now scattering, you know, do some just of, you know, to leading order, right? You can now start to compute things to higher orders. So you can look at final states, which are not just, you know, gluons in final state, but you can look at things like photons coming out from the quarks and so on. And so there's a significant amount of terminology which is now going to higher orders in perturbation theory in this recoupling framework, which you can now solve to next to leading law calculus. And so this describes data from the EIS collider era, from the heavy ion collider Regge, let's see, so on. And in principle, we can do precision tests of this physics at the electron ion collider, which is being built at Brookhaven in the future, in a decade or so. And so one can really test all of these ideas with very high precision. So as I said, that part of the achievement in this program is that you can replace calculations of very complicated amplitudes by shockwave calculations, which are semi-classical. And so you can ask the question, what happens now when you collide two shockwaves? Okay, so imagine there's two nuclei at very high energies, and you're colliding two nuclei at very high energies, right? How do you kind of describe such a collision? Essentially, these are two, you know, very dense blobs of gluons that are being collided, and there's a semi-classical realization of this. Okay? So you can think about now replacing this 2-to-n scattering at very high energies with the collision of two of these blobs, which are characterized by each by colored charge densities. And it's a classical problem, okay? And you can work in different regimes. You can work in a regime where the momenta of the gluon radiation is much larger than this typical scale that's given here by the colored charge density. So you can kind of expand and do analytical calculations in that limit. We call these dilute collisions. And then you can look at a regime where you keep all possible scatterings from one of the blobs of the inclusive radiation, and that's sometimes called dilute dense solutions. And this picture is really kind of described very nicely by this kind of shockwave diagram. So here you have, 1v1 shockwave, which is coming along the light cone. So it's some delta function in this light cone here. So you have highly Lorentz contracted, say, hadron or nucleus along this one light cone with some color charge density. So that's the current. You have another current moving along the other light cone. And the amazing thing is that there's a solution which tells you that before the collision, there are no field strengths produced. So these are so-called field gauges. But then immediately after the collision, we start to produce radiation. Okay, so there's a very nice sort of coherent state kind of picture where nothing is produced before the collision as these shock waves come to collide. So this is replacing your hadrons by shock waves. And so you want to know whether these are actually stable objects. And it turns out that they are these pure gauge solutions, and they produce radiation in the forward outcome. So it turns out that you can compute this radiation of gluons, and this is nothing but the Williams radiation field in QCD. So people will know about the Williams field in QCD, right, which is the field of equivalent photons. You can actually compute that in QCD. And in general, it has a very simple structure, but you see from this classical shockwave calculation that the result is nothing but this Lotto. Remember, I went through this amplitude construction where I showed you that each rung of the ladder, you have the Lotto vortex, which came from summing all these different diagrams. And you do a simple shockwave classical calculation, and you find that the radiation field is nothing but the Lotto vortex times these color charge densities, which are given by the two nuclei. And so this is where these U's are the Wilson lines that I mentioned earlier, which correspond to all possible multiple scatterings of gluons from one nucleus into the other. So this is something that one can do analytically, okay, for the case where you have very large momenta of these reggeized gluons that are being emitted. Or in the case where you have multiple scattering of reggeized gluons from one of the nuclei and only one from the other. So this is called a dilute dense. And the full calculation actually needs to be done numerically. And this is actually what describes quark-gluon plasma formation in this picture at very high energy. So you can take two very high heavy nuclei which are moving at 0.9997 speed of light. Okay, collide them with each other. So it's highly, highly ultra-relativistic. And you can replace that with a function of two gluon shockwaves. It's semi-classical. And you can compute as a function of time, right? Because it's a semi-classical picture, how the system evolves. And you find that you find very non-trivial dynamics in this theory where the system flows to some non-thermal attractor, which eventually then goes to an equilibrium of plasma. And so if you're interested, you can look at this article we wrote some time ago, where we describe all the non-trivial physics of turbulent attractors and hydrodynamic attractors in there. And so another way of looking at this is that you start with some highly out of equilibrium, far from equilibrium shockwave collision process. And then you find that there's a kind of memory loss, and the system flows to some non-thermal fixed point. And this non-thermal fixed point is a turbulent attractor. It has some self-similar properties which are very interesting. And then it goes to some additional quantum kinetic process to thermal equilibrium. And this is several work that Son here did with his colleagues quite some time ago. And a really interesting thing is that you can calculate from first principles in this framework how this very complex system of two heavy ions actually forms a thermalized state. And you see that it depends only on one state. So this extremely complex process of nuclei, which are very complex objects, right? And you find that the thermalization time is just given by some powers of the coupling divided by this saturation scale. And the thermalization temperature is also given by this close package scale. So this is an absolutely beautiful result. And it tells you something very interesting further, is that if you really take the Regge limit seriously, so you say the coupling runs as a function of this separation scale, and it's going to 0. While QS goes to infinity, if you stare at this formula, it will tell you that the system thermalizes almost much shorter time scales in the size of the object that's scattered. Imagine that you have 2 protons that are scattering in principle, and you could describe them by shockwaves. It's telling you that in the Regge limit, you have thermalization on scales which are much smaller than the size of the protons that are scattered. Okay, so because QS goes to infinity, it's much smaller than the size of the proton. So locally, these objects you will have thermalized distributions. And so this is kind of a quite a remarkable result. And I think for a long time, people misunderstood your results because they would say, oh, you know, alpha is very small, so this is blowing up, while QS is some fixed number. But the way to think about this properly is that alpha is a function, is a log in QS. So you have logs in the numerator to some power, and the logs will never beat the power, right? This is the denominator. So when you take QS to infinity, you get thermalization very rapid. So you have really the striking process that you have how thermalization occurs in such a many-body system. So now I want to talk a bit about gravity. And it turns out that exactly the same thing. Or at least the precursor, describe the precursor to how this may happen. So gravity, so now you think, you know, 2 gravitons are transplanted and scattered, and they produce n gravitons, right? What happens? Now gravity on the surface is a very different theory, because if you think about scattering through objects of large impact perimeters, it's dominated by so-called Eichmann scattering. So what that means is that if I think of 2, you know, dust motes at some distance, which are scattering at very high energies, then this leading term is what's the Einstein effect. Yes, it's the famous Einstein term. But now if I say I want to have multiple scattering, as these get closer, then it can be represented diagrammatically in this way, where these objects are Eichmann propagators. So they have the structure which is 1 over p dot k, right? It's not fully off shell. These are Eichmann objects, and you can resum this to all orders. And then the overall Eichmann amplitude for the scattering is given by this Eichmann envelope here, which again also has this infrared divergence. This is the result of all orders. So this is the dominant contribution to gravity. Sorry. But now, what about genuine loop contribution? Right? So the quantum theory, I can compute quantum corrections. So what if I didn't put Eichmann propagators when I allowed these things to be fully off shell? And you can compute that. So this is the 1 loop amplitude. And it has a term which is proportional to the energy squared, S. And it's the log. So this is the Eichmann, right, which I resummed earlier. So this is the log. So it's S times the log. But then there's also this loop contribution, which might seem somewhat familiar to you from the QCD case. But you see there's an S here and there's a T here, right? So in the Trans-Planckian limit, this is highly suppressed compared to the Eichmann amplitude. But you can compute it. Okay? And this gives you same thing that I talked about earlier for the reggeized one. Where you sum all the loop contributions. And it has a Regge trajectory, okay? Just like what you have in the there's an iteration of buttons, and a button there's no when you go to tubes, what is shown by Brookhaven, that's when gravity comes from. There are some tube contributions. But even that is something that is in dispute. So there's some very interesting work by Lance Dixon, the customer, and stories more involved in that case. But certainly in terms of this iteration, in terms of reggeization, so reggeization in gravity occurs at one loop. Okay, so at two loops, there's an open question, if that's the case. And in QCD, for example, we know that reggeization breaks down to one. Okay, so in gravity, whether it works two loops or not, I think is, in my view, still somewhat complex. So this was computed by Lepato 40 years ago. Okay. And somehow this work has not received the attention that it deserves. And so what you find is something really remarkable, which is when you compute all these values, if you sum all the possible real contributions, all the possible work, you sum them to all orders, you find that it's also described by an effective vertex, which is the gravitational Lepato. And it's precisely the following double copy, right? These are the QCD Lepato vertices. It's a bilinear of the QCD Lepato vertex. But then it also has a bilinear of the QED Bremsstrahlung. Okay, so this is nothing but you had QED Bremsstrahlung. It has this form here, right? You might remember it's P over P dot K. Okay. And so that's a QED Bremsstrahlung vortex. And so you need this term as well. And the reason you need this term is actually, it's a little wonkish in the sense that it turns out that there are spurious poles that appear in the X channel when you compute such two diagrams. And that to get rid of those, you need to introduce this additional correction. And as I'll discuss, there's a different understanding of how this arises. But the bottom line is you have this very beautiful double property. So this is an exact relation between QCD and gravity properties. It's really remarkable. So Amati-Chaplin and Vanciano had a very nice power counting of how to think about the S matrix in gravity in this kind of language. So you can exponentiate the S matrix in full generality in this way here. So your leading term into subleading terms. And this term is nothing but the iconal envelope that I mentioned earlier. It's proportional to G times S. Okay? So it's the leading power G times S. And then this delta 1 is suppressed by the Planck square of the impact parameter. Okay, so at large impact parameters, this is a very small contribution. And you can also have, in principle, quantum gravity corrections to your string length, which are of the form some string length over d squared. But if you're at somewhat large impact parameters, these are subleading contributions. But now there's also this additional term here, which corresponds to this diagram that I mentioned here, which are also subleading, but they're subleading in the order of r squared over d squared, where r is the Schwarzschild radius. And so for very large impact parameters, this is much smaller than the iconal term, but and ignore. However, if you're interested in multi-particle production in gravity, this term is absolutely essential. Okay? And so this needs to be taken into account if you want a first principles picture of multi-particle. And my claim is that you can understand all this physics in completely the language of shockwave. So just like in QCD, you have this amplitude construction, and you show that you can cover all this in shockwave. You can do exactly the same thing in gravity, where now you have shockwave collisions in gravity, for which the natural description is this actual metric, where in the metric you have this additional term here, F minus, which is now given at high energies by a term, which is again this density of sources that are colliding. So this is nabla perf times the Einstein coefficient k squared, which is proportional to g, and this is the energies of colliding objects here. And there's a delta function because this is the shock wave. And so the problem then, so you have two shock waves, and here now the current is the stress tensor, so it's T minus minus along one electron T plus plus. along the other light cone. And so the way to think about this is, you can think of this mu as the mass of the object that's scattering times the boost factor gamma. And you take gamma to infinity while keeping this object fixed. And so you can do this calculation. And the way you do it is you linearize along this very strong shockwave background, which is given like this here. Okay. You can fix the gauge. And it turns out that a very similar construction happens in gravity. There's also a Wilson line. And this is exactly analogous to the QCD Wilson line at high energies, except now you replace this metric by the gauge fields, and you replace color factors by kinematic factors. And this is generic for these double coupled relations. You replace color factors by kinematic factors, and you get the same results. And so you can actually go through this entire calculation. So I guess I'm running out of time. So you can actually compute, now I have two shockwaves in different light cones, and you can compute the shockwave production for the light. So in gravity, just like in QCD, you have pure gauges in either side. So the Riemann tensor is 0 on either side of the thing. The difference, though, is you have this Shapiro time delay. So when you have a projectile that comes in, scatters of a heavy object, gets shifted from the light cone slightly this direction here. Right? So that's the B plus operator that you have in the Wilson line. So you have this, this B plus factor here. And that's nothing but Shapiro time delay. So you can actually solve Einstein's equations around this background. You can linearize it, compute in light cone gauge, and you get such a interesting solution here. So this looks like a wave equation, which is then sourced by these additional terms. And so there's some differences which appear to QCD, is that unlike in QCD, you need subiconal corrections to achieve the full solution to the equation of evolution. And so these are these contributions, Ti plus Tij, and they're not uniquely fixed by energy momentum conservation. You have more equations than conservation wants to tell you. And so what you have to do is to find a way to solve for the source evolution. And this is described by so-called geodesic, non-geodesic. And so if you have null geodesics, you can parameterize them by a so-called affine parameter here. So this is the geodesic equations. These are the Christoffel symbols that describe this evolution. And null means that this object x dot squared is 0. But you can solve these equations, and there's an explicit solution to some order in the density of these sources. So these sources are mass densities, and so you're expanding the powers of the mass densities of the colliding objects, and you can do this systematically. And so you can reconstruct the missing components of the energy momentum tensor called the light cone. So you can solve the full problem fully onto the light cone. So, and voila, for the gravitational field, you recover this gravitational orbital. So it's the exact analog of the QCD result. So remember, I secured gluon radiation equivalent to shockwaves, right? It's the inclusive gluon spectrum. And it was proportional to a Levato vertex times these factors. These are the Regge's gluons that contribute to scattering. And you have exactly the same thing for the gravitational radiation field. So if you're trying to ask the question, when I have two black holes or two dust motes, which provide very short impact parameters, producing lots and lots of radiation, what is the inclusive spectrum? As they get closer, it's described by this expression. And this is, as I mentioned, this is precisely this bilinear distribution. Okay, so you can ask, is there a double copy relation? Is there a kinematic duality in general in this case? And it turns out that there is. Okay, so you can start with QCD. So you look at QCD radiation, this classical picture. And so these describe so-called Wong's equations. If you have two classical charges, they're scattering, they're producing radiation. They're described by the Yang-Mills equations, and then you have precessing color charges that are scattering. So these are the so-called classical Wong equations, right? They would be such classical equations. So this is the force term that's proportional to mu times the velocity. And using this, you can compute classical radiation. Okay? And this was something that was done by Goldberg and Ridgway. And they computed the gluon radiation spectrum. But now this is for arbitrary velocities, not ultra velocities. Any velocities you knew, you have this full solution. Okay. And then, but then if you take the ultra relativistic limit, all that survives is this contribution here, because these additional terms, which are dot products of these color sources, charge densities is suppressed by energy. So now if you do a classical color kinematic replacement of the result of Goldberg and Ridgway, so you replace classical color sources that are carrying with momentum labels, you replace the color factors, the structure constants by purely the QCD1 vertex, just the momentum part of it, and you replace the QCD coupling with the gravitational coupling, you recover precisely the this gravitational. So you see that there's an exact kind of kinematic duality, which gives you kind of the result you get. So I'm running out of time. So what can we do next? So we can actually compute the gravitational wave spectrum in GR as a function, of these for this particular case where these black holes getting very close to each other. And this is much more efficient in some ways than doing numerical relativity. So I think numerical relativity, then as you try to go to higher boost, gets more and more numerical. And what we're doing in some sense is we're expanding around finite infinity. So infinity. And there you can actually calculate things analytically to various limits. And so we can actually then take the gravitational spectrum we computed and compute the energy spectrum. And so the solution of this Lopata equation will tell us then how this changes as function of impact parameter. So the principal profile. And amazingly, this hasn't been done. So this is something that we are working on. Hopefully we'll have an answer soon. You can also now understand the case when the black holes are getting closer. So if you have a dust bolt that's carrying a black hole or a star that's inspiring to a black hole at shorter distances, there's a lot of gravitons that are being coherently exchanged between that object and the production and the black hole and the production of radiation, right? And so the question is, can one actually try and compute that? So this is principle, this is something that we can do. And finally, if you compute shockwave propagators on field, so these are so-called graviton reggeized graviton propagators, and you do the same thing in QCD. You compute these high-order computations, and so we need this actually to derive an RG, just like with the scale RG or double RG. And so the ingredients are the Whiteman propagators in the background field and London corrections to the radiation the shockwave background. There's a significant complication, which is very interesting, is that when the dust motes get very close, right, it's actually geodesics, right? That's the approximation which I was working in. At some point, you have to include the fact that these geodesics are bending very significantly towards the focal point. And there's a very interesting picture in terms of shape fluctuations with geodesic and shear forces that one has to take into account. And this is actually a key ingredient in these black hole singularity theories that people have. But in our case, it may not be necessarily to go that far to derive such an RG, but you definitely, I think, have to think about how one implements the Raju equations. And so the outstanding question is there a non-trivial merges starting from this kind of large impact parameter, we can see how things evolve in terms of RG evolution, right? You see that there's not a real fixed point, the gravitational radiation theory. How does one describe that in some systematic way? So that's the outstanding problem. So sorry for all the technical problems and glitches. Thank you very much.
So your gravitational Wilson lines, are they generated by the diffeos? By diffeomorphisms?
Yes.
So how do you do gauge gauge fixing in the gravitation?
So when you do further calculation, you fix a particular gauge.
You said light cone gauge.
Yeah, you fix like the gauge.
Yeah.
You can work in the under gauge also. You can see immediately from the equations of motion that you have such motion.
Yeah, but it's, you have to select like a preferred geodesic, is that right?
Sorry.
In order to work in light cone gauge, you have to select a geodesic, a preferred geodesic. Not necessary.
Yeah, that's only to, so this is really solution to Einstein's equations, right? So it's, but then to understand the source terms of these just like intensive electric walls, that's where we do this. So to really compute the set of equations. So, but the geodesic equations are not a full story. So they are, so one has to really, in principle, to think about, so imagine that you have many dust motes that are scattering, producing information. And so what I'm treating them as whirlwinds, essentially, which are kind of non-interacting, right? Their own geodesic vectors. And I'm replacing them by some mass densities, right? And that's how I'm solving some systematic approximation, the solution to that equation. But at some point, I have to take into account that these mass densities are also evolving, right, as a function of RT. And that evolution is described at some level by these Regge. And so, because, geodesics are a good approximation only for very small trajectories, right? So
But
they're not.
geodesic, that's like in the, when you're considering like the coherent state, like when you're taking the semi-classical limit, right?
Yeah, so it's just a point particle
Yeah.
solution in a
Yeah.
curved background.
Right.
Okay. And so you can have time-like, space-like, or null geodesics. And null geodesics, so it's like a proper time evolution. Right?
Yeah.
But if you have null geodesics, it's defined by this affine. Right?
Yeah.
And so you have, but geodesics are not very accurate, right? Or because the system can go to a focal point that's very shortly plots, right? And also stacks. And so you have to modify these, and that's the Regge equation. And so it's really the Einstein-Regge equations that we solve in the semi-classical. And the question is there an RG that emerges?
Because you're describing gravitational shockwaves.
So we bring gravitational waves, but then you have the conserved currents, right? You can have PDU, right? And then you want to understand how those evolve in the forward way. That's where the geodesic. Because just the conservation laws are not sufficient to fix all components of these systems. That show up in solutions of the gravitation. And gas and
Well, that's them.
Sorry for all the glitches here.